Okay, everybody, I think you should now be seeing my screen. So I am projecting my screen. So I'm actually connected remotely using TeamViewer to our demo system in Santa Barbara in California in the States. That system is actually set up with two monitors, a left and right side monitor. I've only got a single monitor on my laptop here. So I'll be using this back and forth switching between the two monitors over there. So I'll be explaining as best as I can as I go along what I'm doing. I'll take you through a quick step through or walkthrough of the general features, and then we'll get into some real sample measurements. So on what is normally our left-hand screen, what you see here, this is where all of our data is captured and stored, and this is where you'd be manipulating and exploring your data. On the right-hand side screen is where is our live view. This is where you're kind of doing things, setting parameters, and so on. So I'm going to switch off the fluorescence for a second. So we have these tabs here. We have the navigate, spectra, and image tabs, and it's a general workflow process. So you would start off by navigating your sample, you may collect some spectra, and you may then go on to do some images. So at the moment, and if I look through here, we have different mounted objectives. We have a 4-position motorized turrets. We have a Cassegrain 40x, 50x glass, 10x wide field glass, and we also have a glass compensated objective in there. Some focus controls, waypoints are quite useful. This is where we can set positions, prior and saved positions. I've got some samples in there, so I'll be using those in a minute. It's also a cool feature as well. This is our navigate. So this is just a graphical representation of our sample stage in the microscope, everything being fully controlled, remotely controlled. Once you've got your samples loaded in here, everything is done remotely from anywhere in the world, really. And this is an insert. It's basically a 1x3 inch, what would normally be a glass slide, or this could be a sample holder, and I have some samples mounted in here. We also in the back here have some reference samples and also some positions on which we do some backgrounding. But I'm going to be measuring just as a starter on PET. And so I'm currently on my 10x objective. I can actually zoom out as well. We have 3 levels of zoom. So we just see some dust on that. But because of our measurement we use our Cassegrain, so we'll switch back to the Cassegrain objective. Then I'll just raise the objectives and then lower them down again. There we go. I seem pretty happy with that focus there, I might say. Maybe we'll tweak that a little bit. Yeah, I think it's a little better now. I will take a picture of this. And that picture is actually sent, so I'm switching my monitors now, sent to the document window there. I'll come back here, and since I've captured my image, my visible image, this is my spectral acquisition page. So you can set it such that you collect only IR, in which case only IR relevant parameters are made available. You can collect only Raman, so this is a fully functioning standalone Raman spectrometer as well. Or you can collect, my personal favorite, you can collect IR plus Raman. Right, so just to give you a sense on the reproducibility and the speed of which we collect things, I'm going to set what we call an array. I can define a number of points to collect on here, as I've done there. If I clear them, I could even just draw a line along there, and you can set the number of points and the spacing between those points, or I might even fancy a little mapping experiment where you might have not 15 micron spacing, but maybe some 1 micron spacing, and you'd be collecting a hyperspectral. But in the interest of time, let's just say maybe we can do 3 random spots like that. I can even start Raman here just to see how that's looking. I can start my IR QCL laser, and that will be emitting at 1450, so I have a little bit of a response there. But I'm going to collect those 3 spectra. We'll only do one averaging for the IR and 2 for the Raman. So let's start that. And I'm going to go across to the other monitor, and you'll see now spectra appearing as we go across. Right, so that's the first spectrum, first point, second spectrum, and the third will come up. And it's also a nice demonstration of the complementarity, isn't it, really? Because you can see that this main carbonyl peak is active in both IR and Raman, and there is another peak here whose sort of designation or band assignment I'm not too familiar with, but that's clearly not active at all in the IR. It's also a nice demonstration of the difference in sensitivity between the two, the IR being offering much better sensitivity than the Raman. So that was really our quick and easy sample. So why don't we move on now to a little microplastic sample I've got sitting here. Let's go to these 1 micron PMMA beads. And these are, yeah, as the name states there, these are 1 micron PMMA beads sitting on a calcium fluoride window from memory. Why don't we just tweak the focus on that? Maybe something like that. So I can explore that. You may even want to go back to your 10x objective. So it gives you a much better view there. But I will come back to the Cassegrain. That's where we'll be doing our measurements from. And this is where we'll do our first feature finder. Right. So there we go. So at that point, in fact, what I will do, I like to have my experiments separated. So I'm going to start up a new document. And this will be for my 1 micron poly PMMA beads. I'll capture a picture of that there. And this is here is our feature finder button, or open feature finder it says. So if I click on that, that window opens up in the other pane. So now we see ourselves the picture that we just saw on the screen there before, the little histogram there of all of those pixels. And we'll just modify these just to make these points a bit more clear and more obvious. And with that, I can also set filter by size, so you can ignore either the large ones or the small ones and set a range. But if I hit calculate, if I come back and accept that, it's now giving me markers for all of those particles, right? So you can now see crosshairs on all of those particles. And if I hit acquire array with IR plus Raman selected, it'll go off and collect those. So I'm hitting acquire array. Let's go back to the previous window and we'll see what unfolds. So there's our first infrared and Raman spectrum. I might just give it a few runs here, and then we'll come back and we'll abort that. Then we'll do our measurements, or rather our identification process. So you can see it takes about 3 to 4 seconds per spot. All right, I think we get the gist of it now. So I am going to go back to this tab here and abort that process. Okay. And just to give you an idea on then the second phase of this, so once we've got our points measured, let's highlight the spectra that we want. So let's just search these ones. If I go into analysis and chemical ID, I'll just set that to 1800. You can now, so we've also got Raman spectra in there, which we don't have in the library, but you can see on the right-hand side our overlay between the collected measured spectrum. Remember, these are 1 micron PMMA beads with a single scan. So that's about a second's worth of collection for a 1 micron bead. And then you've got your hit quality index, you've got circularity, perimeter, size, and so on. For these are, I believe, total area. So I will accept that, and then all that information will be stored in the metadata. Right, so that was our relatively easy 1 micron, and I kind of say that probably is you would have never imagined a 1 micron experiment to be quite easy. The other sample, I'm just conscious of time. The other sample I want to show you guys here is, what's we got? I don't think I'll show you the algae sample. The fluorescently labeled PMMA bead, I think, is a good one. let's go over to that. All right, there we go. So we'll just zoom out a little bit. So there are 3 levels of zoom. You can zoom out this far, low mag, so low zoom, medium zoom, and then maximum zoom. So we'll stick in maximum zoom since these are quite small particles. All right. So this is just a visible bright field at the moment image of this. So I'm going to switch on our fluorescence module, and that starts off with the bright field. So now these cubes are active. I know for a fact that this particular material is works best with M-cherry. Right, so that now becomes, so that's our fluorescent M-cherry image. I'll just give you some contrast, come back to the visible, the bright field, and that's what the bright field looks like. So I'll just take it, this in fact is a new document, so let me go back and collect a new one, or create a new one rather. I like to save as many images as I can because I can go back and explore them. And that's our M-cherry image. So why don't we take that? Remember, if you recall in the presentation, I said that it's not just the visible images that we can give as inputs into FeatureFinder, but we can also use fluorescent images also. I'll do that this time around. We've got, in fact, what I'll do is, I don't want to work on this cluster here. Let me go back and turn that off. So the cluster, why don't we go find ourselves some more nicely isolated particles. Maybe one of these. Sure. Tweak the zoom, tweak the focus rather. Great, I'm happy with that. Let's take a picture of that. Fire up FeatureFinder. And I'll switch back over here. Pull these back. And it gives us particles. Right, so at that point I can say calculate. I can accept that. And these are fluorescent, so which means your Raman channel will be awfully fluorescent. I'm going to turn the Raman off. I'm only going to do IR here. Let's go off and collect this array. Okay, so I've come back to the left-hand side monitor. So these are PMMAs. Okay. Select a few of those. You can see it's about a second per spectrum. And there's a second or so of sort of stage movements. Right. That's probably enough at this point. So I'm going to go back and just abort that. I think you get the idea and the process here. So I'm going to abort that. We could all just go back and do a quick chemical ID search on those, just to reinforce that. And of course, they've all come back as PMMA, not surprisingly, right? But you know, again, these are I think are now 2 micron particles. They might be a little bit larger than the other ones, but the spectral quality, and this, I mean, this is a single scan. These are 1 to 2 micron particles, and look at the spectral quality. I think it's astonishing. I've been doing infrared spectroscopy for 20 years, and it never ceases to amaze me just how good the spectral quality can be. Okay, so that was our fluorescent example. So remember, and try and picture how you may do this, or you take advantage of this in your experimentation. So if you were able to fluorescently label your samples, your polymers, if you imagine that there were 100 particles in here and only 10 of them, or even 5 of them, were actually polymers, if you'd labeled them with Nile red, they would then be sticking out like this. And there would be only polymeric materials that would be standing out in the fluorescent image. All of the other rubbish, all of the other sand, mussel shells, or bones, or cellulose from trees, they would not be visible in the fluorescence. So it's a great way to optically, fluorescently filter your samples and then you collect spectra only from the plastic. So I'm quite enthusiastic about that. So now, how about we try a more real-world microplastic sample? So I'm just going to switch off the fluorescence module, and we'll go to our waypoints. That would be MP1. And in order to better locate our sample, I'm going to switch to the 10x. In fact, with this particular sample, it's a larger field of view. So we're going to actually collect the visible images on which we perform our feature finder on a different objective to the one that we actually do the spectroscopic measurement with, which is the Cassegrain 40x there. So here we are. So that's our live image. We've got some particles on a gold-coated polycarbonate filter. That's our bright field image. I'm going to switch over to the cross polarizer. So in fact, I didn't need to turn the fluorescence off. And you can see now, so this is a good example of how the cross polarizer really helps light these particles up. So in fact, why don't we go back to the other screen? And as always, let's create a new document. Come back here. So I'm happy with that. So why don't we just fire up Feature Finder? That goes into the next page. I'll just tweak some of these. Accept that. So come back over to here. All right, so now we've got those particles marked. And so these are irregular shaped particles, all mix of particles, and these have been filtered directly onto the polycarbonate filter. So we're carrying on the 10x as I hit the acquire button. In fact, how about I hit the acquire button, and then I'll tell you what it's doing as it's doing it. So because we're in the 10x objective, it's going to just raise that up now, switch that around to the 40x. So we'll see, in fact, this 10x in a second, go to the 40x, and there it is. And it will perform an autofocus on this particular sample because these samples are quite irregular in height, unlike the other beads. Right. So it looks like we've got a nylon-like spectrum for the first one. So we'll do a few of these. I am conscious of time, and then we'll just abort it like we have for the other ones. Okay. So you can see the signal noise is actually really good. I could have probably gotten away with fewer scans on this one. 1 or 2 scans even would have been enough. So we'll do maybe just 2 more. So we'll switch back and abort that now. Coming back to our screen over here, if we highlight these spectra, open up the ChemID, just tweak that to 1800, which is what we've collected over. We can have a look at some of our match results. So we can see nylon, polystyrene, and polystyrene, and some more polystyrene there. So spectra generally match well. We can accept that, export that to a CSV, etc.